Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 5, Lesson 9 on solving systems of equations algebraically. In the last lesson we introduced you to what a system of equations was, and for us in Math 8 it's simply going to be two equations of lines that when we graph them, we're trying to find their intersection point. It's that simple. What we're going to be looking at today is how you can find that intersection point by simply using algebra. And that's often how systems are solved in the, quote, real world. We solve them with algebra in order to find the intersection points. It's not so much that we graph the two and find the intersection point. We do it mostly with algebra. So let's jump into it right now, solve one graphically, and then also see how to solve the same system algebraically. Now the key to solving a system of equations will be what we call the substitution property of equality. And by the way, you've used the substitution property of equality many times in mathematics. It basically just says equals may be substituted or replaced by equals in any expression or equation. So like for instance, the number 5 is equal to 2 plus 3. So if I ever felt like it, I could replace the number 5 with 2 plus 3 because 2 plus 3 and 5 are the same thing. Like in this equation of this line, if I really wanted to, I could replace 10 with 15 minus 5 because 15 minus 5 and 10 are the same thing. It's just called the substitution property of equality. Equals may be substituted for equals. Anyway, let's take a look at exercise number 1. Let's not worry so much about that substitution property of equality for right now, because in exercise number 1, what we want to do is we want to solve this system. So it says, consider the system of equations shown below, y equals 2x minus 2, and y equals negative x plus 10. Letter A, solve this system graphically. All right, well, this was the entire thrust of our last lesson. You should have gotten lots of practice on it in the homework. Why don't you go ahead and graph this line, find their intersection points, write it down. You don't have to do the check like we were doing in the last lesson, but go through the process and, solve the system graphically. All right, let's do it. Both of these lines have sort of their own challenges, right? So in the first line, right, in y equals 2x minus 2, right, we have a slope that's equal to 2 over 1 and a y-intercept that's equal to negative 2. So I'm going to go over here to negative 2. On the y-axis, I'm going to go to the right 1 and up 2. All right, that's going to produce a bunch of points that I can then connect with a straight line. Well, let me do that. All right, never forget that when you're graphing two or more lines on a coordinate grid, make sure to label them with their equations. So this is my y equals 2x minus 2. All right. Then my other line, also a little bit challenging because I might want to write it as negative 1 times x plus 10. That's going to tell me that my slope is negative 1 over 1 and my y-intercept is 10. I'll go up here to a y-intercept of 10. Down 1 to the right 1, down 1 to the right 1, etc., going through all those diagonals on our squares. Again, let me just shrink down my ruler a little bit, rotate it. Well, that was almost the right rotation, not quite. And let me draw that line. Okay, get my equation labeled, not the greatest line drawn, but we'll live. Here's my intersection point, and that's at 4, 6. Make sure to circle that answer, 4, 6. All right, we could easily verify that that is the answer, by substituting the 4, 6 into both of these equations, showing that it makes both of them true, but we don't need to do that. Now let's move on in letter B to the thrust of the lesson. Let me just kind of move this up a bit. All right, let's take a look at letter B. Solve this system algebraically by substituting one equation into the other using the substitution property of equality. So in other words, write y equals 2x minus 2. Since y is equal to this, we can replace or substitute for this y this expression. So literally, what I'm going to do when I solve these equations algebraically is I'm going to take this expression for y and I'm going to substitute it into this expression. And that's going to start me off with 2x minus 2 is equal to negative x plus 10. Now, one of the big advantages of doing this substitution is, number one, I go from two equations down to just one. And the second thing is I go from two variables, i.e. x and y, down to a situation where I have only one variable. Now, these types of equations we've solved already. We solved them a bunch back in Unit 1. And we also solved them throughout the course. But let's review a little bit, right? We've got variables on both sides. We can either move sort of like all the numbers over here and all the x's over here, or we can move all the x's first, then all the numbers second. I think I'm going to first move all my x's to this side by adding an x to both sides, right, to get rid of that negative x. 2x plus x is 3x, so I get 3x minus 2 is equal to 10. I can now move that negative 2 to the other side by adding a positive 2 to both sides, right? That's going to then give me 3x is equal to 12. And now I can divide both sides by 3, and that's going to leave me with x is equal to 4. Now I want to just pause for a minute. Take a look. X is equal to 4. Look at the solution to our system. What's the x value? 4. Right? There it is. Now, how do we produce the y value? Well, the y value tends to be very easy, because all we need to do is take this x value and either substitute it into this equation, which will produce the y value, or this one that'll produce the y value. In fact, if you substitute them into both equations, that's a fantastic check. So we're going to maybe do that just in this one problem. But technically, since we're just looking for the xy pair where they intersect, once we have that x value of 4, we can put it into either one of these equations to find the y coordinate, and then we have our point of intersection. Let's take a look at that, right? So we've got these two equations. One is y equals 2x minus 2. Let me just kind of rotate this out of here. So let's produce the y coordinate by substituting the x coordinate into this equation, right? And then, of course, we've got 8 minus 2. And y is equal to 6. Now, you don't have to do this next part, okay? But I'm going to do it anyway just to kind of show you, right? The other equation that we had was y equals negative x plus 10. This is a great check, because if I now put my x equals 4 into that equation, I can see that, in fact, y is also 6. If I had gotten these two y values to be different, right? If when x was 4, I got a different y value here than I did here, then I would know that I kind of made a mistake getting this. Because remember, this is supposed to be a point that's common to the two lines. If for a given x coordinate they have two different y coordinates, then that cannot be their intersection point. But here we can verify very easily that they are, and in fact, there it is, right? X equals 4, y equals 6, x equals 4, y equals 6. It's that simple. Right? We use the substitution property of equality to substitute one equation into the other. And you might say, well, how do I know I should put this one into here instead of this one into here? And the answer is, it just doesn't matter, right? It's going to result in the same equation. Maybe like the left side will be on the right side and vice versa. But at the end of the day, when you solve that equation for x, you will get the x coordinate where the two lines intersect. Let's continue to look at that. Although, quite frankly, that's really the entire lesson. When we substitute one linear equation into another, we oftentimes refer to it as setting the equations equal, because that's kind of what it looks like. Let's go through number 2 together as well. Exercise number 2. Solve the system of equations below algebraically. Show your work. All right, so no graph grid. You know, even if I had a graph grid, this one would be kind of a pain to graph because its y-intercept is down there at negative 17. But algebraically, it's as simple as this. I'm going to take this expression and I'm going to substitute it into this y value. So I'm going to have 3x minus 17 is equal to negative 2x plus 8. Now again, just before we go on to solve this, technically speaking, what I'm doing is I'm using the substitution property of inequality. But you will have a lot of math teachers, including maybe the one that you have right now, who says, set the equations equal to each other, right? Because that's what it looks like. I'm taking this, 3x minus 17, and I'm setting it equal to negative 2x plus 8. The reason I'm doing that is because I'm substituting this expression in for this y, because that's what y is equal to. Now it's pretty easy to solve this equation, so what I'd like you to do is solve this equation, get a value of x, substitute it into either one of these to generate the value of y, and you will have solved the equation algebraically. Go ahead. All right, let's do it. And again, whether you choose to sort of move the numbers over or the variables over, whichever order you decide to do that really doesn't matter. I'm going to stick with what I did before. I'm going to add a 2x to both sides to get all the x's on one side of the equation. Those will cancel. 3x and 2x is 5x. I get 5x minus 17 is equal to 8. I'm going to add a 17 to both sides. That's going to give me 5x is equal to 25. Maybe I'll bring it up here just so that you can see it better. 5x is equal to 25. I'll divide both sides by 5. That cancels, and my x is equal to 5. That's the x-coordinate of intersection. Where's my y-coordinate? Well, I can take either one of those equations, so I'm just going to take the first one, and I'm going to substitute x in. 3 times 5 is 15. Right? I now have 15 minus 17, which is negative 2, and that's the y-coordinate where they intersect. So if I had a graph paper and I graphed both of these lines on it, they would intersect at the point 5, negative 2. And an excellent check would be to take the 5, substitute it into one of the two equations that you didn't put it in to get that value to see if you still do. So like for me, we won't write it all down, but if I took the 5 and I put it in here, I'd get negative 2 times 5, which would be negative 10 plus 8, which would be negative 2. Good check. All right, let's keep going. Solving a system of equations that involves fractions can be tricky when done algebraically, right? Because fractions make life more difficult. They just do, all right? So let's go back to our graph grid. Let's again solve a system of equations graphically that involve fractional slopes, and then we'll go back and solve it algebraically, which will get a little bit ugly because of these fractions, but we want to make sure we can get through it. So let's take a look at exercise number 3. Consider the system of equations shown below. Y equals 3/2 times x minus 3, and y equals negative 5/4 times x plus 8. Letter A, I just want you to solve it graphically. So pause the video now, graph both of these lines, make sure to label them with their equations, circle their intersection point, write it down, and then we'll go through solving it algebraically. Pause the video now. All right, excellent. Well, let's take a look at this first line. Let me just move this over here, maybe make it a little bit smaller. Right, my first line has a slope of 3/2 and a y-intercept of negative 3. So we'll go down here. Whoops. We'll try to just move the ruler. Bring this up a bit. Y-intercept of negative 3. 2 to the right, 3 up. 2 to the right, 3 up. It starts to sound weird after a while. All right, let's bring down our ruler. Rotate, maybe make it a bit longer. And there's my first line. All right, simple. Y equals 3/2 x minus 3. My next line, also pretty easy to deal with. M is going to be negative 5 divided by 4. B is going to be 8. So I'm going to go up to a y-intercept of 8. I'm going to go to the right 4 units, down 1, 2, 3, 4, 5. Right 4 units, 1, 2, 3, 4, 1, 2, 3, 4. Of course, it's got to be right where I have my ruler, 5. That'll be enough. Let's bring it up here. Rotate my ruler. And great. No. Why do I keep doing that. There we go. Don't grab the line. Y equals negative 5/4 x plus 8. There's our intersection point at 4, 3. All right, so we've solved our system graphically, right? Simple enough and pretty easy to do, right? Because the slopes are easy to interpret, the y-intercepts are fairly easy to interpret. Now let's do this thing algebraically. Now again, if you have a choice, if your teacher gives you a test or you're on some kind of state exam and they give you these two equations and they give you a graph grid and they say, hey, solve this system, and they don't say you have to do it graphically or algebraically, pick whichever one seems easier to you. Oftentimes for me, if the slopes are fractional, it's easier to do it graphically. And if the slopes are whole numbers like they were in the last problem, then it seems to be that it's easier to do it algebraically. But to each their own. Let's take a look at how we do this thing algebraically, and let's do it together. So I'm going to take this expression and I'm going to substitute it in for this, and I'm going to start right here. 3/2 x minus 3 is equal to negative 5/4 x plus 8. Now, unlike the last couple problems, what I'm going to do is I'm going to start by moving my numbers over all to the right-hand side. So I'm going to have 3/2 x equals negative 5/4 x plus 11. All right, so let's just step back for a second. That's the easy part. Of course, the harder part is now going to be to get these x's over here. Now, if that was 3x and negative 5x, I'd add a 5x to both sides, right? The fact that it's 3/2 x and negative 5/4 x doesn't change what I'm going to do, it just makes it more difficult, right? Because what I've now got to do is, let me extend the page a little bit, is I've got to add a 5/4 x to both sides, right? And whereas it's natural to just say something like, oh, 3 plus 5 is 8, it's a lot harder to think about what 3/2 x and 5/4 x are. But that's really all about what 3/2 plus 5/4 is, right? We know with fractions we have to have common denominators. The most convenient common denominator on this one will be fourths, and specifically we'll get 11/4. So 3/2 x plus 5/4 x is 11/4 x, which is sitting an awful far away from the equal sign. But again, keep in mind, right, when we combine like terms, we're really adding or subtracting their coefficients. Here I've got 3/2 and 5/4. I change the 3/2, so it's 6/4. I add 6/4 to 5/4, I get 11/4, and we're all the way over here, right? Maybe I can move this a little bit closer. Nope, I can't. Oh well, worth a shot. So now I might as well just erase all this. Now, of course, I still have to solve for x. I'm going to do that with this trick of multiplying both sides by the reciprocal of that fraction, right? And that's going to make all this stuff cancel. And now one of the beautiful things is these 11s will cancel, and I'll get 1 times 4 over 4 times 1. That'll be 4 over 1, which means x is 4. All right? Remember, we already solved this system graphically, and look at that. The x-coordinate where they intersect is 4. Now, let's be very clear. What's making this algebraic solution harder is only 2 things. Well, it's really only one thing, the fractions, right? But the 2 things that make it harder is obviously combining the 2 fractional terms like this, and of course solving it once we get down here. Now, once we've got that x equals 4, now we do exactly what we did before. I'm going to take my 4, I'm going to substitute it into one of these 2. Given that this one doesn't involve quite as many negatives, I think I'll just use this one. So let me do that. Now I'm going to have y equals 3/2 times 4 minus 3. Let me just kind of put a little dividing line in there. Okay, the 2 goes into 4 2 times. So now we'll have y equals 3 times 2, which is 6 minus 3, and y equals 3. Right? And that's exactly what we found up above, right? The solution algebraically was the intersection point 4, 3. What I really like about the algebraic solution to systems is that you can really see how the algebra gives you exactly the same answer, right, as the graphical. Exactly the same answer, but using a completely different technique. All right, let's get a little bit more practice on solving systems algebraically with two problems, right? One, which is going to be pretty easy because our slopes are whole numbers, 4 and 1, and one of them that'll be harder because our slopes are fractional, 2/3 and -1/6. What I'd like you to do, pause the video now and try to solve letter A, then we'll go through that. That should be the easier one mechanically to do. And then we'll also have you pause the video and try to work through the one that's harder because of the fractions. Pause the video now and try to work just through letter A. All right, let's go through it. So my first step when I solve a system algebraically is to substitute. So I'm going to put 4x minus 26 into that second equation, setting those equations equal. 4x minus 26 equals x minus 8. Maybe I'll stick with the same order I did before. I'll add 26 to both sides. Be careful here, right? It's really -8 plus positive 26, which will be positive 18. Then I will subtract an x from both sides. 4x minus x is 3x. I'll get 3x equals 18. Divide both sides by 3, and x equals 6. Now to get my y variable, I can substitute it into either equation. I'm going to substitute it into this one. That seems very easy. I'll just have y equals 6 minus 8, and y equals -2. So hopefully you got 6 (-2) in that problem. All right, now for the more challenging one, the one with fractions. So what I'd like you to do is, again, pause the video, take your time. If you struggle combining the two fractions, which you'll eventually have to do, look back at the previous problem to see what we did, but see if you can work through it, and keep in mind you will get nice sort of like integer answers for both x and y. Pause the video now and take a few minutes. All right, let's go through it. Really, the procedure is exactly the same, right? There's really nothing much that's different. The thing that's going to be more challenging is that work with the fractions. So I've got 2/3 x minus 3 equals -1/6 x plus 7. All right, let me get that arrow off of there. Again, for me, I think I'm going to move my numbers over first. So that's going to give me 2/3 x is equal to -1/6 x plus 10. Here comes the hard part. Now I've got to add a 1/6 x to both sides, right? And this is where it kind of can get tricky, right? Because you've got to somewhere figure out what 2/3 plus 1/6 is. Now again, the most convenient denominator in this case would be 6th. So 2/3 plus 1/6 is 4/6 plus 1/6, or 5/6. All right, I'm just doing all that on the side of my paper. So I now have 5/6 times x is equal to 10. Just like before, I'm now going to solve this by multiplying both sides by the reciprocal of that fraction, or 6/5. Again, if that's confusing, put that 10 over 1. 5 then cancels into 10 2 times. I have 2 times 6, which gives me x equals 12. Now that's the x-coordinate, that's the x-coordinate of the intersection, x equals 12. To find the y-coordinate of the intersection, I want to take the 12 and substitute it into here or here, whichever one you feel more comfortable with. I'm going to take it and substitute it into this equation. So let me kind of do that. That's going to be y equals 2/3 times x minus 3. Just bring the screen up a little bit more so you can see how the work gets finished off. 3 cancels into 12 4 times. Y then will be 2 times 4, which is 8, minus 3. So the y is 5. All right. Again, this second problem is mechanically, step by step, no different than this one. We set the two equations equal, right? We then solve for x. The challenging part there is the fact that we've got these, fractions that we've got to combine, and then the algebra is a little bit more difficult to finish up. But once we have our value of x, we do exactly what we did in this problem. We take that value of x, we plug it into one of the two equations to produce the value of y, and eventually we get our intersection point 12, 5. All right, let's wrap this up. So today we saw systems of equations for the second time, right? In the last lesson we learned just what a system of equation was and how to solve them by graphing the two lines and finding their intersection points. Today what we did is we looked at how we can substitute one of the linear equations into the other one to eliminate the y variable. Then once we've done that, we can solve for the x variable, right? Just solving an equation with x's on both sides. Once we have that value of x, we can then take it, substitute it back into one of the two original equations to find our y coordinate. This is all based on what's called the substitution property of equality, one of the most important properties of all inequality, which basically just says, hey, you can substitute equals for equals at any time you want in a math problem. All right, we're going to get a little bit more work with systems of equations in the last lesson of this unit. That's the next one. But for now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.